Good morning. You can all see the screen. Can you see the screen? This one?
Yes, sir.
Good. So we were discussing non-deterministic finite automata. Okay. And as we saw, they're very similar to deterministic automata. The only difference is that delta is a mapping from Q cross sigma to the power set of Q. And everything else is the same. And we took an example to illustrate the behavior of non-deterministic automata, but we didn't define the behavior formally. So that's what we are going to do today. So first of all, did we do this? We didn't do this, right? Anyway, even if we did it, there's no harm in repeating that. So first of all, we extend delta the transition function to delta hat. So, and this is along the same lines as deterministic automata, but we have to be careful now because given a state and a symbol, there's a set of next states. So this is the inductive definition. For the empty string, the set of states that are reached is just Q, the set containing Q itself and nothing else, right? And for a string, which is of the form UA, where U is in sigma star and A is in sigma. This is, again, remember that this is a set. So this is the union of all the sets of the form delta RA, where R is a state in delta hat QU. Okay. So this is an inductive definition because this string UA, the value of the function on this string is expressed in terms of the value of the function for a smaller string. This can be written in another way. this is just the set of states P such that there exists R belonging to delta hat Q U and P itself belongs to delta R A. So it's important to understand this. And if you have any doubts, you can ask me now. So this is the meaning of delta hat. Delta hat QW is the set of all states that M, the NFA M, can possibly reach. After reading the input string W starting from state Q. Any doubts on this, on the definition? And often we drop the hat and we just say delta, right? So given this definition, we say that M accepts W if delta Q naught W intersection F is non-empty. Remember, this is a set. This is a set of states. And this is really delta hat. Right? So if this says that M accepts a string W if it is possible to reach some final state after reading W starting in the initial state, right? And then the language of M is W delta Q naught W intersection F is non-empty. I think we went up to this point in the last class. Any doubts? So the next obvious question is, does the notion of non-determinism give us anything extra? Okay, so we want to compare the expressive powers or the expressive power of DFAs and LFAs. Okay. It turns out that we don't gain anything in terms of language acceptance by going from deterministic to non-deterministic automata. Okay, so we cannot recognize more languages uh, by invoking non-determinism. Okay, so there are two propositions which capture this fact. First, the easy one: for every DFA, M there is an NFA N such that the languages accepted by the two are the same. Why is this the case? Because intuitively, every DFA is also an NFA, where uh, the possible choice of next states is exactly a singleton set. So for every symbol and every state, if in the DFA you have, and let me write it this way using the subscript, if you have QA, if this is Q dash, then in the NFA, for Q and A, you will have the singleton set containing Q dash, right? And everything else is the same, right? So this effectively means that every DFA is also an NFA. So clearly, the language accepted by M and N are the same. But this is true the other way as well. For every non-deterministic finite automaton N, there is a sorry, I'll just write DFA M such that the languages accepted by the two are the same. And there's a little bit of history behind this proof. This proof was first given by Dana Scott and Michael Rubin when they were interns at IBM Research Center in Yorktown Heights. And this was either in the late 50s or early 60s, I don't recall. And Dana Scott and Michael Rubin are both Turing Award winners in computer science. They work in slightly different fields. But I'm sure you'll see at least some of Michael Rubin's works in later courses, if not Dana Scott's. But anyway, let's come back here. So they investigated the power of non-determinism, and they showed that, at least for finite automata, non-determinism doesn't give you any more power, right? And the construction they give is called the subset construction. Also sometimes called the power set construction. So this is a famous result in computer science, and it is relatively easy, unlike many other famous results, right? So how do we do it? Well, let's start with an NFA n. Okay. And so let me write Q. Everything is subscripted with n. Q sigma is the same. Delta n, Q0 n, and Fn. So this is the NFA. And we are going to construct a DFA from this NFA such that the DFA accepts the same language, okay? So how do we define it? Well, yes, how we do it. The set of states of the DFA is the power set of the set of states of the NFA. Okay, that is, it is the set of all subsets of Qn, meaning a state of the DFA M is actually a set of states of the NFA N. Okay. Intuitively, this is because after reading an input string, the NFA N could possibly be in a set of states, right? In any one of a set of states. So the DFA actually keeps track of that. For every string W, the DFA will keep track of the set of states in the NFA that can possibly be reached after reading W. And that is why the set of states here is the power set of Qn. So a state here is a set of states of Qn. That is the idea. Of course, we have to prove that these two set the same language, the same languages, right? And so let me write Q0M and FM, where we already have described the set of states delta M. Okay, you have a set of states P. A state here is a set of states original non-deterministic automaton. This is simply the union of any questions about this? How this is defined? So remember, this capital P is a set. It's a set of states in the non-deterministic automaton, which means that if you call this it is an element of Qm. So this is defined as the union of delta nqa. And remember, this is a set for every q and a. Delta qa is a set because n is a non-deterministic automaton. So take the union of all those sets as q ranges over p, right? So intuitively, this means if you have this set P and on a symbol A, you can go from here to there and from here to there, from here to there. Then you take all these states that can be reached by starting from a state in the set P, right? Um, by a transition in N. Okay, that is the meaning. Okay, so this whole thing is a set again. So this is again an element of QM. Any questions on this definition? Okay. Yes. Then you tell me what should the initial, sorry, this should be M. What should be the initial state and what should be the final set of states? Anyone? Sorry, why did I write a 0 there? That doesn't make sense. Can anyone tell me what should the initial state be in the DFA-M?
So the
It
power,
should be equal to initial state of NFA.
It cannot be the initial state of NFA. It
so
has to be a
power set,
set,
so
not
power
power
set.
set, not power set. It has to be a set containing the initial state of the NFA, right?
Yes, sir.
And what about the set of final states?
Sir, power state of Fn, power set of Fn.
No.
So it should be containing Fn.
It is the set of all states. Sorry, it is the set of all sets. Let me use P, etc. other than X. Okay, so any state which has a final state of n as an element is a final state. And remember, a state here is a set of states in the non-deterministic automata. Right? So any
Sir, shall this be QM in the definition of FM? P is a subset of QM.
this one, it is n. If P is a subset of Qn, then P is an element of Qn.
Okay, sir.
Any subset of states of n that contains a final state is a final state of n is a final state of m. So I just wrote it down in words. So is it clear now? There was something in the chat. I didn't see that. Can you use your mic to ask that question? Or comment or whatever? Yes? I didn't see that chat comment. Please. Please use your mic. In case you have any doubts or comments. See, intuitively, this is how it works. The DFA M will keep track of all the states that can possibly be reached by the NFA after reading an input string, okay? And if any one of them happens to be a final state, then the string is accepted by the NFA, as we said. Therefore, the DFA also accepts that string, and that is this condition here. Right? This is the condition. Because this condition says at least one of the states in the set P is a final state in N. So is that clear or not? Of course, we'll do the proof. But before we do the proof, you should have the idea clear in your mind what this DFA is doing. It's actually simulating the NFA. And after reading an input string, it's keeping track of all the possible states that can be reached. Is that clear? Okay. Then without further ado, we need to show that the language of M is the same as the language of N. Okay. In fact, we show a stronger result, which is just writing down in mathematical notation what I just stated. We will show a stronger result. And what is that result? That is, for all strings W, delta M Q naught W is the same as delta N Q naught W. Why is it a stronger result? Because this particular result, Lm equals Ln, actually follows from this. How does it follow? Well, you just apply the notion of final state here and the notion of in the DFA and the notion of acceptance in the NFA. So the NFA accepts this word W if and only if the right-hand side of the equation has a state in F. So that is a set. The right-hand side of the equation is a set of states because this is an NFA. And if that set of states contains a final state, then and only then is W accepted. And similarly, on the left-hand side, you accept W because this is the DFA if you reach a final state. And what is a final state? A final state in the DFA is a set of states in the NFA which contains a final state of the NFA. So Lm equals Ln follows immediately from this result, right? Any questions on that? And how do we show this result? Any guess? How do we show this result? Yes? Sorry, I didn't hear that.
By induction
By induction on what?
on the length of the word.
That's right. So by induction, on the length of the word W, right? So the induction basis or the base case is that the length of W is 0. That is, W is the empty string, right? In that case, what is the left-hand side? Oops. The left-hand side of the equation is delta M Q0 epsilon. Of course, you know that what we really mean here is delta hat. So this is really delta hat. Because we are talking about a string here. This is a string. So this is by definition just the state which is the singleton And this is by definition of delta hat for DFAs. We gave an inductive definition. Delta hat Q epsilon is just Q, right? Here, of course, each state is a set of states. So whatever you have here, the result is that state, which is a set, right? So no problem. What is RHS? Well, if you go back to our definition of delta hat, for NFA, here it is. It's just the set containing Q. Q naught, right? So both sides are equal. Let's come to the inductive case. So here we assume that the statement holds for all W with the length of W equal to N. And we are going to show it for any string with length N plus 1, right? So assume, so if a new string so for any string W, which is of length N plus 1, so A here is a symbol in sigma. So the length of W dash is N plus 1. We got to show that both sides are the same, right? So that's what we got to show, assuming that the result holds for W because W is of length N. So this is how we proceed. We proceed with the left-hand side. This is just delta M Q0 WA. And remember, this is delta hat. Okay. So let me write it just for ease of understanding. So we follow the usual inductive definition of delta hat for DFAs. So this is nothing but delta hat M. Sorry, this is delta M, delta hat singleton Q0 W comma A, right? This is by definition of delta hat for DFAs. And what can we do now? What is the next step?
The
Oh, I
delta
forgot
hat
to
of
write
Q
M
not
here.
comma W is same as like delta hat of N of Q not comma W.
Right. So this thing here, we can apply the induction hypothesis. That's what you're saying, right? You're saying we can apply the induction hypothesis because W is of length N. So we can write delta M delta hat N what is the result we are proving? This is the result, Q0W. Oops, still not. This is by the induction hypothesis. Does anyone have any questions on this? I'm just applying the induction hypothesis. So by induction hypothesis, these two are same, okay? This is the induction hypothesis. Yeah? Then what? Then I apply, so this is a set. This is a set of states in N, okay? And then I just apply the definition of delta M itself. Yeah. This is by definition. This is the construction. This is how I define M. So delta MPA is union of all those, right? So it is just to look at it again, union of Q and A over all Q belonging to this set, right? So this is a union of delta N, right? Q A, where Q belongs to delta hat n q0 w, and this is by the definition of delta n. What is the next step?
Apply definition of delta n.
Delta hat n, right?
Yes.
So this by definition of delta hat n is q0 wn. If you want to see that, well, I have to scroll up and do all that, but you can do it. I mean, if you just try to recall how we define delta hat for strings, it was an inductive definition, right? First for the empty string epsilon, and then for any string WA, right? And this is the way, exactly the way we did it. So that's it. This is the right-hand side. And as I said, the main result that LM equals LN follows from here, right? So let me also write it down. So once we have this, then W belongs to the language of LN if and only if delta hat Q0 W is a state in FM and this should be M, and by the result we just showed, if and only if delta hat N Q0 W belongs to FM, then we apply the definition of FM. FM is the set of all sets of states which have at least one final state, right? So this is the same as saying by definition of FM, acceptance by an NFA N, and this is via DFA. Any doubts? Well, if you have doubts, I suggest you read the proof carefully. You sit down, and spent some time going over every step, because this is important. This is one of the most important results in the theory of finite automata. And it's essential that you understand the proof, right? And this course is all about proofs. So you should understand this proof thoroughly. And if you spend some time, that'll be well worth the effort. So the question is, we showed that DFA and NFA have the same power. Then the next question is, why use NFAs at all? And what do you think is the answer?
Easy to draw.
Yes, in the sense that often the NFA is much smaller. Even exponentially smaller. Okay, and to illustrate that, think of this language, ln. The nth letter from the end of W is a 1. Remember our friend ln? And we showed, what did we show? We showed a result, remember?
At least
About
2
this-
to the n states.
Huh?
At least 2 to the n states.
Any DFA recognizing ln must have at least 2 to the power n states. But this is a DFA. What about an NFA? How many states do you need? Yes? Any guess?
N states.
Well, n plus 1 actually. So 0, 1, 2, and so on up to n, right? This is a final state. So the automaton just guesses at some point that the one that is seeing is the nth letter from the end. And after that, it doesn't matter whether it's a 0 or 1. Yeah? And so on. Do you understand this? So it has n plus 1 states. And that is exponentially smaller than the states of the DFA. So this is the power of non-determinism. You get more succinct. Please learn this word if you haven't heard it before. Succinct. Because the number of states is much fewer. Okay, so let me stop there. And I'll put up the solutions to the quiz problems today. All right, let's stop.